In today's note, we are going to be looking at exponential decay. So this is very similar to exponential growth. However, instead of our relationship growing, it's going to be decreasing or decaying. So just to start us off, what is the sale price of an item before tax if the advertised price is A, 20% off the regular price of $50? So if I want to figure out what the sale price of this is, I need to figure out what is 20% off of $50. So there's one way I can do it. I can take $50 and I can multiply it by 20% or 0.20 to figure out how much I'm actually going to be saving. And when I calculate this, 20% of 50 is $10. So then therefore I can do 50 minus 10, which equals 40. So that means that my sale price is going to be $40. Another way I could do it, if I want to simplify it and do it into one step, I could think about if I want to find the price of something and it's 20% off, how much of the original price is it? And if you think about it, if we're taking 20% off, then that means we're basically paying for 80% of our price. So I can figure out the sale price by doing 50 times 80%, which equals 40. So we're kind of doing it in the reverse way of thinking not how much I'm going to take off, but how much am I going to have left. I'm going to have 80% left of my original price, so it's going to be 40. So let's try B. 30% off the regular price of $189.99. So if I'm taking 30% off, how much am I going to have left? And if we're not sure, we can think about it this way. If I multiply $89.99 by 1, that gives me the original price, or 100%. I'm going to subtract 30%, or 0.3, and when I multiply that, I should get my sale price. So when I simplify it, I'm basically multiplying $189.99 by 0.7, or 70%. Because if I take 30% off my price, I'm paying for 70% of it. Or 70% is how much I have left. When I go through and I calculate this then, I get $132.99. So that means the sale price, when it's 30% off, is $132.99. Or you could think of it as 70% of the original price is $132.99. So that's kind of the idea that we're going to be working with in this case, because we're decaying or we're decreasing. So number 2, the value of an Austin Matthews hockey card is $18, and it depreciates in value by 20% each year. How much will the card be worth after 1 year? So we can do the same thing. We can do it as one calculation. The price of the card, it's $18 originally, but because it loses 20% each year, it's going to be 1 minus 0.2, or basically 18 times 0.8, because it's only going to be worth 80% of its original value. And I get $14.40. So after 1 year, the card is going to be worth $14.40. Well, how do I do it for 2 years? I could take the $14.40 and do the exact same thing. So the price is going to be $14.40 multiplied by 0.8, which I know is what the worth is going to be. It's going to be 80% of the original price, or the price that it starts at, and I get $11.52. Now let's say I didn't know what the year 1 worth was. I didn't know that it was going to equal $14.40. How could I use the original value to figure out how much it's going to be worth after 2 years? And this kind of ties into our last lesson on exponential growth. And if I look at the original price, I know it's $18. After 1 year, it's going to depreciate by 80%. So 18 times 0, or not depreciate by 80%, sorry, but it's going to be worth 18 or 80% of your original price. So 18 times 0.8 will give us the year 1 price. If I multiply it by another 0.8, it will give me the year 2 price. And hopefully you can start to see the connection between exponential decay and exponential growth. So if I want to continue this pattern or relationship and fill out my table, I know year 1 was 18, or sorry, year 0 was 18, so original value was $18. After 1 year, it was $14.40. After 2 years, it was $11.52. How do I figure out the third year? Well, I could go back to this patterning, $18 times 0.8, and because it's 3 years, I'm going to multiply by 0.8 3 times, or to the power of 3. And after 3 years, I should get that it's worth $9.22. For 4 years, 18 times 0.8 to the power of 4. $7.37. 5 years, exact same thing. 18 times 0.8 to the power of 5, because it's going down by, or it's worth 80% of the original value for 5 years. And then 590 is our 5th year. The ratio, again, same idea as exponential growth, y2 divided by y1, so basically the bottom minus, or bottom divided by the top. So 1440 divided by 18 gets 0.8. 11.52 divided by 1440 I get 0.8. And if I continue this pattern, I'm going to get the same amount, because the ratio tells me what the growth rate is, or in this case, the decay. So if I want to graph these values, it starts at 18 at 0 years. At 1 year, it's 1440. 2 years, it's 1152. 3 years, it's 9. 4 years, it's 737. 5 years, it's 590. If I graph it, we can see that it's not quite linear, and it's almost the opposite of our exponential growth. In this case, it's decaying, or it's decreasing. But it's not a straight line, it has a curve to it. Write the equation relating y, the value of the card, and n, the number of years. So very similar to what we looked at before, we had to multiply the original value, 18, and we multiplied it by 0.8 to the power of n, or how many years we are looking at. So what is the value of the card after 15 years? Well, y equals 18 times 0.8 to the power of 15. And here I should get 0.63. Or basically after 15 years, it's going to be worth 63%. Will the card ever be worthless? Will it ever be worth 0? And if you think about it, can I put this to the power of anything and get 0? And the answer is no. So it will never be worthless. And the reason is because the only way I can get 0 is if whatever I multiply 18 by has to be 0. So is there any way I can get 0.8 to an exponent of 0 by increasing the exponent? No, because the only thing, if I look at my exponents, if I think back to my exponent rules, there's no exponent that will make my base 0. The only case would be if the base itself is actually 0. Right, so you could think about if I did y equals 18 times 0.8 to the power of 1,000. Right, that's not going to work out to 0. There's no exponent that makes the base 0. So this card will never be worthless. Or you could think about it, if I'm always taking 20% of something, I'm never going to get to 0 because I'm always just going to be taking smaller and smaller amounts, and my value is going to get smaller and smaller and smaller, but it will never equal 0. So this is an example of exponential decay. So it's the opposite of exponential growth, and we can kind of see that in the equation. The equation for any exponential decay is y equals a times 1 minus r to the power of n. A is still that original amount, or the starting value. R is still the rate of decay, or basically the percentage as a decimal. And n is the number of periods, in this case the number of periods of decay, and y is the final amount. The only key difference here is that I'm subtracting. I'm subtracting that rate of decay, or that percentage, from 1. So let's kind of work through some examples to get used to using this in an actual equation. So the population of Slum City is 5,000 people. What will the new population be if Slum City decays at a rate of 3% per month for 12 months or 24 months? So here, my A is my initial value, or my starting value. How many people do I start with? I start with 5,000. What's my R value? What's my rate? Well, it's 3%, which is actually 0.03 as a decimal. How many periods are there? Well, it's for 24 months. So in my equation, y equals a 1 minus r to the power of n. A is 5,000. 1 minus r, or 0.03, to the power of n, or 24. This just works out to a calculation. Make sure we do our brackets, then exponents, then multiplying, and we should get 2,407. So that means after 24 months, we'll have 2,407 people. For B, same idea. Even though the units are changing, that's fine, because the rate is still per year, or the rate and the number of periods is the same, or it's the same unit. So our A value is 5,000. Our R value is now 8%, which as a decimal is 0.08, and our N is 7, because we're looking at 7 years. So Y equals 5,000, or A, times 1 minus r, or 0.08, to the power of n, or 7. And we should get 2,789. So that means after 7 years, decaying at a rate of 8% per year, we'll have a population of 2,789. Number 4, Connor's brand new car has a value of $30,000. The value of this car depreciates by 12% per year. What will the value of the car be after 6 years? So, if I look at my A value, what's the initial or original amount? In this case, it's 30,000. What's my R value, or the rate? Well, it's 12%. We need to turn it to a decimal, so 0.12. And the N, or the number of periods in this case, is 6, because we're looking at 6 years. So in my equation, y equals a 1 minus r to the power of n. Plug in our information, so y equals 30,000 times 1 minus 0.12 to the power of 6. If we want to, we could simplify. 1 minus 0.12 is 0.88 to the power of 6. So basically what it's saying is that after every year, my car is going to be worth 88% of the value of the previous value. When I solve, this just becomes a calculation. Make sure you do your exponent first, then multiply. You should get $13,952.12. So therefore, the car is worth $13,952.12 after 6 years. So this might be important to know if you're looking at when you should sell your car, because it does depreciate. The cars do depreciate at an exponential rate. Right? So right after the first year, it does decrease by quite a bit. So just looking at another concept, when a population cuts in half, or if we decrease by half, it is said that it is said to decay at a rate of 50%. So if our population is getting cut in half, it decays at a rate of 50%. So the last example, the population of lorax, an endangered species, currently is at 12,000 worldwide. Every year the number of loraxes in the world is cut in half. What will the population be 6 years from now? So my A value is the original amount, or what I start with, which in this case is the 12,000. My R, or my rate, is 50%, which works out to 0.5, and my N is 6 years. So in my equation, y equals a 1 minus r to the power of n. Y equals 12,000, 1 minus 0.5 to the power of 6. I can simplify my bracket. 1 minus 0.5 is 0.5 to the power of 6, and y then equals 187. So after 6 years, the population will be 187. What will be 8.5 years? Again, same idea. Our original amount, or starting value, is 12,000. Our rate is 50%, which we convert to 0.5, and our n is 8.5 years. So in my equation, y equals a 1 minus r to the power of n. 12,000 times 1 minus 0.5 to the power of 8.5. I can simplify my bracket to just 0.5. And when I solve, I should get 33. So after 8.5 years, I will have 33%, or not 33%, sorry, 33 individuals left. So again, the main idea from this lesson is just understanding how exponential decay works, how it's similar to exponential growth, and how we can use the equation, or sorry, the general equation, to come up with a relationship for given situations. So again, being able to identify the original amount, determine the rate of decay and change it into a percent, and then use that to figure out what our final amount is going to be. Again, it's very similar to exponential growth, except instead of adding the rate, we are subtracting the rate. So that's why we see the minus r instead of plus r. But again, very similar to exponential growth because they are kind of opposites of each other.